But today we look at what a limit is and the definition of a limit. Now, this is sort of not a true mathematical definition, would have lots of little symbols and more complicated words, but we're going to just sort of have a basic idea definition that a limit is a value that you can get arbitrarily close to. So in our notation, we write a limit with the words LIM, and then say, what is the limit of this expression when x gets really, really close to 5? So as x gets closer and closer to 5, 3x minus 8 gets closer and closer to 7. Does that make sense? I mean, if you plug in 5 exactly, 3 times 5 minus 8 is 7. And if you can plug in the number, you evaluate the limit. It's that simple. What's going to be more complicated is when we get into somewhere we can't plug in the number. So in this case, what's the limit of 3x minus 8? When x gets close to 5, we'd say that it's equal to 7. If you put in 4.99, you would be a little bit less than 7. If you put in 4.999, you'd get even closer to 7. So the first thing we're looking at is how do we evaluate limits? So a couple of definitions. Our first definition is continuous. Most of the functions that you have dealt with in math until now, polynomial functions, are continuous. Again, this is not the official math definition of continuous, but this is just a way to have it make sense. A function is continuous at a point if the graph can be drawn without having to lift your pencil. You can see why this would not be in the official math dictionary. Oh, here we go. Official math dictionary. Yes, of course, everybody has to have one of these. Didn't you see it in your course outline? Yeah, good. All right, continuous. Continued, continued product, continuity, continuous distribution, continuous function. So the official definition out of a math dictionary, continuous function. I will only read the first 2 paragraphs, not the page and a half definition that's in the definition. It starts here. Will appreciate my definition of not having to lift your pencil compared to this. But a function for which a small change in the independent variable causes only a small change and not a sudden jump in the dependent variable. A real function f of x is continuous at x equals c if the right hand and left hand limits of f of x at x equals c and f of c all exist and are equal. Otherwise, f of x is discontinuous at x equals c. An equivalent definition is that for any positive number epsilon, a positive number delta depending on epsilon and c can be found such that the absolute value of f of x minus f of c is less than epsilon. That made so much more sense than my definition, right? I'm sorry. I should really work on my wording. But my wording says that something like an x cubed graph is continuous, because I could draw the whole thing without having to lift my pencil. But if I had a graph that went like this, right here, we would have a point of discontinuity because you had to lift your pencil to keep drawing. You couldn't keep drawing without lifting your pencil. So a line, a parabola, a cubic function, those are all examples of continuous functions. You could draw your sine graph without lifting your pencil forever, right? And so that would be an example of a continuous function. Right? Sometimes, and you have seen some graphs, do you remember graphing these ones in grade 12? Oh, I'll write the equation. I'll factor the top already for you. Do you remember graphing that in grade 12? X plus 4 times x plus 2 over x plus 2. What happened? The x plus 2's simplified, and this just became y equals x plus 4. And you graphed that originally in grade 10. That's a straight line. That's a straight line with a y-intercept of 4 and a slope of 1. However, at negative 2 comma 2, there was a hole, because in the original equation, if you plug in negative 2, you divide by 0. And dividing by 0 is not allowed. So in that graph, you graphed a hole. Technically, if you were trying to graph the whole thing, you'd have to lift your pencil when you got to the hole and go to the other side of the hole and keep drawing. And so we would say that that hole makes it not continuous at that point, because you couldn't draw it without lifting your pencil at that point. Right? Which means you're not allowed to use pen in this class ever, because then this definition doesn't work. I'm kidding. Good. All right. So if a function is continuous and it exists for all values, you can evaluate a limit just by plugging in that value. So for example, x squared minus 1. That's a continuous function. That's a parabola. Has no breaks in it, no holes in it. So if you were evaluating this limit, when x gets close to 2, what does x squared minus 1 get close to? Well, you just plug in 2. 2 squared is 4 minus 1. We would say that that limit is equal to 3. If we just dealt with continuous functions all year with limits, then you just have to plug numbers in and everything would be easy, because it would just be like going back and like figuring out function notation. Okay, I'll get it to you next class. Perfect. So discontinuous, we've talked about that. A function is discontinuous if you cannot draw the graph without lifting your pencil. For example, at an asymptote or a hole, it would be discontinuous. And in some equations, like this one, this would be a graph that would be a line, because those x minus 3's would cancel out, and you would have a hole. So if we wanted to find the limit as x gets close to 3, currently we can't, because plugging in 3 would cause us to divide by 0. If we graph that function, we already saw in the previous example, you would simplify these away and just be left with x plus 3. So you'd have a y-intercept of plus 3, a slope of 1, and a hole, oops, not there, wait for it. A hole when x is equal to 3. Perfect. And if I want to figure out where that hole is, I would plug in 3 into my new equation, and I'd have 3 comma 6. The idea of a limit says limit as x goes to 3. Here's my x value of 3. If I get closer and closer to 3 from the left side, can you see that my y values are getting closer and closer to 6? And if I came from the right side and got closer and closer to my x value of 3, my y values would also be getting closer and closer to 6. And so what's going to happen in limits like this one, where initially you can't plug in the value of 3, after you've simplified it, all that we'd be left with is x plus 3, after you've simplified it, if you can plug it in now, then you can say the limit will be 6. Notation-wise, when we're writing down limits, we keep the limit notation, limit x goes to 3, until you're at a point where you plug it in. So at this point, I know that I can plug in 3 without dividing by 0 or doing something illegal in mathematics. And I can plug in that 3, and 3 plus 3 is 6. So I can say the limit of this function is 6. And often we're looking at that in saying, what would happen as I get close to that x value? Does my y value go to something? Now, the reason that this section was titled 0 over 0 limits is because if we look at this equation to begin with, this equation to begin with was the limit as x goes to 3. If I even multiply out the top, it would be x squared minus 9 over x minus 3. What happens if you plug 3 into your denominator? Obviously, you get 0 on the bottom. What happens if you plug 3 into your numerator? You get 0 on your top. And when this happens, 0 over 0, often a limit exists, but you can't find it out right away. In this case, we had to simplify until we could plug it in. And that's a strategy we're going to be using for a lot of these. We're going to say, is there a way that I can simplify this so that I could plug it in? So discontinuity, in the example that we just did, we would say that that graph has a discontinuity or a hole at x equals 3 because the function is not defined at that point. Next example, we've got the limit as x goes to -2. If you plug -2 into your numerator, you'll get 0. If you plug -2 into your denominator, you'll get 0. So we can't evaluate this limit right now. Okay? The other thing, unlike the previous graph, do you know what this graph looks like? When you see it, does it like a graph come to your head? Good. Because one doesn't come to my head either. That looks very complicated right now, doesn't it? Right? Well, now I see it. Looks like a straight line. But that does not look anywhere near a straight line that we're used to, does it? So what do we have to do? We have to come up with some way of simplifying this. And often that way of simplifying that we've used through math all the way through is if we can come up with a clever way to factor this. In our numerator here, we have x cubed plus 8. So you're going to have to start to recognize, hey, that's a no, not a difference, a sum of cubes. It's x cubed plus 2 cubed. And we can factor, so as far as our work goes, we can factor the top to be x plus 2 times something, all over x squared plus 6x plus 8. No, it doesn't look like a line. I thought it was going to look like a line. It doesn't. I was getting all excited. Just disappointed. What goes in there? And we're going to factor the bottom too. I'll start with factoring the top. Because I was kind of, at first, I was hopeful that whatever went in here matched up perfectly with that. But does it? Well, to get the x cubed, this would have to be x squared. To get the 8, this would have to be the 4. There'll be minus 2x in the middle. It didn't match with the bottom. So Eric's right, we could look at the bottom as well and say, is there a way I could factor that? So I go limit as x goes to -2. I have my x plus 2 here. And the bottom factors out nicely to be x plus 2, x plus 4. And one of the most enjoyable pastimes in math is after you've factored something out. Oh, that feels good. Canceling out the factors. And what's amazing about canceling out that factor, can you see that that's the factor that was causing us issues? That's the one that made it 0 in our numerator and 0 in our denominator. And now my expression, could I plug in negative 2 now? Yes. Because if I plug in negative 2 now, my denominator is just going to be 2. And my numerator, this will be 4 plus 4 plus 4. And the limit as x gets close to 2 of that expression will equal 6. I mean, we can see from the graph that as x gets close to negative 2, it really looks like it gets close to 8. There's a little bit of a problem in this graph because this graph technically should have a hole there. But Desmos probably has a hole there. You just can't see it because it's so tiny. Because the pixels are bigger than that hole would be. It's just like that small. Just a tiny spot that doesn't exist. But there would be a point of discontinuity there because if you plugged in negative 2, you'd be dividing by 0, which is not allowed. So when we show our math, we factor. Once that factor comes out, anytime a factor cancels, that creates a hole in the graph, except in some situations, but I'm not going to go into that right now. Most of the time, when the factor cancels out, you get a hole in your graph, and then you could plug things in and evaluate, and we could say this limit is equal to 6. Oh, so much good math happening here. Your job, when trying to figure these out, is to use your skills in algebra. You need to get rid of that h on the bottom. Because right now, if I plug in 0 for h, I divide by 0. So I'm going to get you to try this one. Use whatever algebra skills you have. See if you can come up with a way to simplify this so that that h goes away on the bottom. So probably the most typical technique that comes up with is multiplying the h minus 3 squared out, which is h minus 3 times h minus 3. That's what squaring means. This is all over h. And if I distribute all of this, I'm going to get limit. And we have to write this limit as h goes to 0 every single time until we can apply and plug in the 0. So if I multiply that out, I'm going to get h squared minus 6h plus 9 minus 9 all over h. Well, the 9 minus 9 goes away, and I'll be left with just h squared minus 6h, which has h in common. So I could factor that h out, leaving me with just h minus 6 all over h. Yes, and cancel out those h's. Feels so good. After you've canceled out those h's, you would now be allowed to plug in 0 for h. And the answer is just minus 6. Probably the most common method is expanding it out. Okay? So I'm going to take that method. Oh, yeah. There we go. Make it a little small. There's method 1. Method 2, switch colors, go green. Another method that I saw walking around, some people noticed that the top was a difference of squares. It's something squared minus 9, and 9 is something squared as well. And so if it's a difference of squares, we can factor it as h minus 3 and h minus 3 plus 3 and minus 3 all over h. Notice how I use the brackets, right? Sometimes you have brackets inside of brackets. You can decide to go square brackets and round brackets. I like to go big brackets and then not quite as big brackets if I have brackets inside. It helps you see, oh, these little brackets go together. And it helps you see these big ones go together. And it makes it a little bit clear. Now, if we simplify the top, well, minus 3 plus 3, this just becomes h. This just becomes h minus 6 over h. Wow, that's pretty. H's cancel out. Get that feeling of enjoyment again. And it's equal to 6. Method number 2. And then what I really liked is someone chose a method that didn't go anywhere useful. It's not that it's a bad method, but this is true in math. Sometimes we come up with an idea and we want to try it. I have done this so often when trying to solve a problem. I come up with an idea and I try it, and every time I take another step forward with the idea, things just get worse. I try it a little bit longer and it gets worse and worse. And sometimes you have to make a decision that since it's getting more and more complicated, maybe I have to go back to the beginning and try something again. So the idea on this one was multiplying by the conjugate, which is a brilliant thing to make that connection because a lot of these deal with multiplying by the conjugate. So if we do that, the bottom becomes h times, and I'm not going to multiply it out, I'm going to leave it factored. And this is important, some important things. If we were going to multiply by the conjugate, hoping to cancel out the h, it makes sense to leave the h factored out so it's easier to cancel. Okay? If I multiply out the top, I'm going to get h minus 3 to the 4 minus 81. Whew. And this is where this step, at this point you go, now what could I do? Nothing really nice. Because now if I want to expand this, h minus 3 times h minus 3 times h minus, it gets complicated. So you might see at this moment that you're like, it's not, is that, I don't know if that's the proper spelling of but I think it's close. Yeah, it's problematic. So we go, okay, I'm going to scrap this method for now. I'm not completely going to put it out of my mind because somewhere else it might be really, really helpful. But sometimes in math, we try something that gets complicated. And sometimes in math, we have to go through a complicated step where we think this can't be the right way. And then we find out later on, yeah, I had to do that complicated thing to get to the right step. And that's really messy, because I've been through that. I'm solving a tough math question. I try the complicated way, and I go, oh, this is not nice at all. And I scrap it. And I go back to another method, and it doesn't work, and it doesn't work, and it doesn't work. And I'm like, oh, I have to try the complicated way again a little bit longer. And I go a little bit longer, and I'm like, no, this is ugly. So I try other things, I try other things. And sometimes I've gone back to that complicated method the third time and finally worked it all the way through, and it's like, yeah, it did work. But I wanted to find a better way. But if you allow yourself to try those different things, right? Here, this first blue way and the green way both work. The green way ends up being really kind of pretty when it simplifies. Okay? Sometimes the green way doesn't work and the blue way works better. but having more than one option can help you see, in some cases, a better solution. And that's what I like about math, is you can figure out something one way, but then you think about it a little bit, and you're like, oh, there's another more elegant way to do it. And then you go, oh, there's a really long-winded way that works that I would never want to do, but I figured it out anyways. All right, here's one to try. You have to get rid of that x on the bottom. Right now it makes you divide by 0. All right, let's look at this one. And the beautiful thing about this one is the key strategy that's going to help you is the same strategy that led us nowhere in the last question. Trying to multiply by the conjugate in the last question didn't help us. But having that in our mind, for this one, if I multiply the top one by its conjugate, and this is where in the previous stuff you're like, well, when would you ever want to rationalize a numerator? Well, this is your example. Multiplying by the conjugate gets rid of square roots in a binomial. And so at this point, if I multiply out the top, I'm going to get x plus 16 times x plus 16 squared. Oh, that's hard to say. But you're just going to get x plus 16. And the difference of squares will be a minus, and 4 times 4 is 16, over. And this is where I would not multiply out the bottom, because I want to get rid of that x. I'll just leave that x by itself and the other factor by itself. What ends up happening in our numerator? Well, the 16s go away. Oop, I forgot x goes to 0. So I write again, limit as x goes to 0. My 16s go away. And now the x's cancel out. Now careful, because this happens so often, and it happened to a couple of you when I walked around, is when you cancel out those x's, you think that this somehow magically just is all by itself. Technically, what happens when those x's are canceled out, you still have a 1 on top. And it's 1 over x plus 16 plus 4. But now, can I plug in 0? Yes. Because I would get square root of 16, which is 4 plus 4. I will get 1 over 8. So for working on questions, and we're going to work on them for maybe 8 minutes, not a super long time. If you haven't brought your textbook, but you have your phone, you can go to that website to pull up the textbook.